Okay, guys. So what we did last time was we covered the work energy theorem, and we're just going to quickly review that before we get into conservation of energy, okay? So what we said in work energy theorem is that the kinetic energy for our system, right? If we have a system, the kinetic energy, and we're going to ignore everything that's in the background here, so maybe let's come down here. Just come over here. Work energy is basically saying that any kinetic energy I have in my state 1 plus any work that's done from my state 1 to 2 is equal to the kinetic energy in my state 2, right? Kinetic energy can be defined or can be separated into 3 separate categories, we said, right? Number 1, we said we can have fully translation, right? So translation. And this is simply 1/2 mv about the point G, right? The velocity, the linear velocity of my body at its point G squared. We can have pure rotation, right? Rotation. And that is defined as 1/2 my moments of inertia about a point that isn't moving, right? And that, for the most part, is my IC, my instantaneous center, right? So 1/2 multiplied by my moment of inertia, my mass moments of inertia about my IC, multiplied by my body's angular velocity squared, right? And last but not least, we have this case where we have both of these things acting, right? Our body is not only translating, but also rotating, right? So that is simply both of these added together. So 1/2 the mass of my body multiplied by the velocity of my body about the point G, the linear velocity of my body about point G squared, plus 1/2 the mass moment of inertia about point G omega squared, right? My angular velocity squared. Okay, that was the basic idea of kinetic energy. And for work we said that it can be separated into 2 separate categories. Work we can have work due to 2 separate things, right? We can have work due to external moments, right? In that case, it would be m d theta, which simply in our case would translate to m theta. That would be equal to the work done caused by any moment, right? And then for the work done due to any force, that would simply be F d, the dot product, right? My force multiplied by a path, right? So it's as simple as that. And then this would later translate to F d cosine theta. My force multiplied by my path multiplied by the angle between them, right? Angle between my force vector and my path vector, right? And that's, in short, how we determine whether it's positive or negative, which is the whole point of those problems, or at least the challenge within those problems, determining whether forces or whether work is positive or negative, right? So that's a quick recap of what we did last time, right? But now we're going to go into something new. We're going to go into a special case of this work energy theorem. And that special case is what we call conservation of energy. Conservation of energy is just work energy theorem with a condition. And that condition is simply that you do not have non-conservative forces. What the heck is a conservative versus non-conservative forces? We'll go through it right now. Okay. We can split the work done on this body. We can take this formula, right? And we can bring it over here. And we can say that this work done is made up of 2 parts. It can be made up of work due to conservative forces and work due to non-conservative forces. So let's write that down real quick. So the kinetic energy plus the sum of the work done due to non-conservative forces, right? Non-conservative, plus the sum of the work done due to conservative forces is equal to my kinetic energy in state 2, right? So that's equal to my kinetic energy in state 2. What the heck is a conservative versus non-conservative force? Well, in short, a conservative force, we'll do an example, but a conservative force, in essence, if you're going to remember it, it does not care about the path that it takes, right? We had that example of the guy free falling from last time, right? The guy's over here and the guy's over here. And this is the ground, right? What forces are acting on him? What main force is acting on him? Gravity, yes, beautiful stuff, right? We have gravity acting on him here, and we have gravity acting on him here. A conservative force is a force that, if you want to imagine it, let's say this guy, he doesn't naturally move like this. Let's say he disappears, right? Disappears from here all the way to here. Poof, magic, right? Gravity will still act on him, right? He will still experience the force of gravity, right? Do you guys agree? right? If he's up here, he still experiences gravity, and maybe even if the ground's over here, he still experiences gravity, right? He doesn't necessarily have to pass through this distance. But think about the force of drag. If he's falling, right, he has to pass through this distance to experience drag, right? He has to move to experience drag, right? Do you guys kind of understand that concept, right? He has to pass through that distance to experience that drag force, right? Whereas he doesn't necessarily have to pass through this distance to experience this gravitational force. Another example we can go through, if that didn't really make sense, is a box, right? We might have a box right here. That's not a box. We can have a good old box. And then you can see that, okay, gravity is acting on this force, right? Gravity is acting on this box right here. And then let's say it moves a specific distance, right? Gravity is still acting on this box, right? It doesn't necessarily mean that I had to move it from side to side. Or let's even say that these are two separate boxes, right? If these two separate boxes are not moving, and let's say there's friction as well, right? There's kinetic friction if these boxes move. Kinetic friction will only act on my body if I translate that box, right? But again, if you want to imagine it, if I make this box from here disappear and bring it over here, gravity's still going to act regardless of whether it moves, right? So look at my hand signals, yeah? Okay, is that understood? Any questions? That's important to know if you move on, before we move on. Questions? Once, twice, 3 times? Okay, yeah? Yes? Yes, a conservative force, it doesn't care about the path the body follows, right? It will always act on the body regardless of the path, right? So again, gravity will act regardless of the path you follow, but kinetic friction will only act if you follow a path. And same thing with drag. Drag will only act if you follow a path, right? Hopefully that's understood. So what is the special condition that conservation of energy works with? Well, that's only if we don't have any non-conservative forces. If we don't have kinetic friction, if we don't have drag, if we don't have any non-conservative force, we can go ahead, we're free to use conservation of energy. Why? Because this guy cancels out, right? And then we're just left with this equation, right? So let's say we don't have non-conservative forces. We don't have forces that the path matters. The path matters in simple terms. Path matters. And then examples, F drag, F kinetic friction. Right? Okay. We can keep on simplifying this formula. What is a conservative force? Well, a conservative force is what we have been dealing with in work energy theorem, right? It's your gravity forces, your applied forces, your I don't know, or applied forces isn't a good example, but your gravity forces and your spring forces for that matter. That's what we're going to deal with. And the simplicity, another thing that we call work caused by conservative forces is we call it potential energy, right? That is potential energy, whether it be gravitational potential energy or potential energy due to a spring, right? So we can write that down. So this formula, once we get rid of non-conservative forces, we get T1 plus this guy translates into V1, right? My potential energy in state 1 minus my potential energy in state 2, right? That's what the work due to conservative forces becomes in this scenario. So we have V1 and then minus V2, right, is equal to my kinetic energy in state 2. And then from this, finally, we get to the final version of the equation, and that is simply T1 plus V1. My kinetic energy in state 1 and my potential energy in state 1 is equal to my kinetic energy in state 2 plus my potential energy in state 2. And if that, derivation, kind of barely derivation, but if that didn't make sense, doesn't matter. Just use the formula, right? It's as simple as that at the end of the day, right? Okay, so this is the wonderful formula we're going to be using. And remember, if there are no non-conservative forces causing work, if you don't have kinetic friction, if you don't have drag, if you don't have any non-conservative force, you can use this formula. You can still use this formula if you have a non-conservative force, but you have to add, right here, you have to account for the work due to non-conservative forces. Right? But I don't think we're going to be dealing with that for the most part. Anyway, I think we're all good. We can get into an example. Actually, let's explain one last thing. Before I do that, any questions? It's important to ask. If you got, yes?
The V1 and V2 are potential energy, right?
Yes, that's what I was going to exactly go into right now. What's your question?
In real life scenario, when would there not be non-conservative forces?
A real life scenario. The examples that we're going to go through, they're all non-conservative forces. But even this, like, obviously there's like some resistance in the pin, but we don't care about that stuff. But anyway, what I was going to go into next is the fact, what this sir right here just said, which is a very important fact. What is potential energy? Well, in our case, we're only going to consider two main types of potential energy, and that is simply potential energy due to gravity and potential energy due to a spring. Does anybody know what the energy due to gravity is? Guesses?
MG.
You guys should not be guessing that. You guys should know that, right? Mg what? H, right? Mgh, since gravitational potential energy depends on your y value, it's mgh, or mg, your displacement in y, from state 1 to state 2, right? So mgh, or mg delta y, I don't really care. What is the potential energy due to a spring? The potential energy due to a spring. It should also not be a guess. You guys should know this.
K squared?
Pardon?
1 over 2 K squared?
Beautiful, yes. 1 over 2, 1/2, the stiffness of the spring, x squared, right? Or delta x squared is the change in, I'll get to you, the change in your strings, or your spring's displacement, right? What's your question?
Is it negative?
It is not negative in this case, right? You can write it as negative, but we're going to stick to this formula, and this formula will do the stuff for us, in essence. We'll get to why it's not negative and all that fun stuff, like, because that's the easiest place to get messed up in these questions, right? You do one cross product wrong, and then your answer is J instead of K, or I instead of J direction. It gets all messed up. So negatives and positives is a very, very important point, but we'll get to that in the question. I think it's easier to explain then. Anyway, we're moving smoothly. We can go to the first problem, which is, you could probably do this without me even telling you, and I hope you can, but regardless, we're going to go through it. So we're going to structure ourselves in a proper manner. We're going to start with our state 1, or our, not state 1, but our step 1, givens, right? If the 30 kilogram disc is released from rest when theta is equal to 0, determine its angular velocity when theta is equal to 90 degrees. So what am I given in this question? We need to be, not like last time, we need answers, right? The numbers are in front of you. What are you given in this lovely question? Yes? The mass, right? So we're given the mass of our, what is this called? A disc? Disc. Mass of our disc is equal to 30 kilograms. We start, our initial theta position is when theta is equal to 0, right? So theta 1 in this case, in our state 1, is equal to 0 degrees. Theta 2 is equal to 90 degrees, right? We start from rest. Right, so our omega 1 is equal to 0 radians per second, and that's all we'll write for now. We can write the radius, right? The radius, let's say from, or our vector, right? The radius in this case is the same thing as our distance from our direction vector, our position vector, from point G with respect to O, right? So what is that position vector? What is that radius? Not actually, let's just say radius. Let's not confuse ourselves, because then direction comes in and whatnot. So position vector is equal to 0. Or our radius in this case of our disk is equal to 0.3 meters. Let's just keep it like that for now. Okay, what am I looking for in this question? Unknowns. What does the question want me to find?
Omega at state 2.
Beautiful, yes, omega at state 2. I want to find my angular velocity at state 2. I don't have to draw a schematic because it's fairly straightforward, but let's do it just for technicalities. Schematic. Right? So in state 1, this angle is going to be 0, right? So our type of cylinder is going to look like this, right? Do you guys agree with that? It starts from rest, and it's going to look like this. Do you guys agree? At least nod your head. Yes or no? Yes? Beautiful stuff. In state 2, what is it going to look like? Well, it says 90 degrees, right? It starts at 0 degrees, and then it goes to 90 degrees. So therefore, it's going to be perfectly if you will say perpendicular, right? Do you agree that it's going to look like this in state 2, right? Okay. So I'm not going to redraw it because this is fairly simple. Do you need me to redraw it? Yes, that's the correct answer. No. Okay. Beautiful stuff. We're going to skip schematic just for time. So we're going to go directly into the easiest way to solve this. In this case is literally conservation of energy, right? So let's start with the formula. So conservation of energy. And you could do this with work energy theorem as well, but conservation of energy, in this case, we're going to see it's much simpler. Any questions so far? Good stuff. Okay. We're going to start with our formula. T1 plus V1, my kinetic energy in state 1 plus my potential energy in state 1 is equal to my kinetic energy in state 2 plus my potential energy in state 2. Do I have any kinetic energy in state 1? Do I have any angular velocity? Do I have any linear velocity? No, right? So automatically I know that this one is 0. I can cross that out. Do I have any potential energy in state 1? Yes, sir.
It would depend on where you set your datum.
Amazing. That is so important. Excuse me. It depends on where I set my datum point. I can do this question 2 ways. I can have potential energy in state 1 and then not have potential energy in state 2. I can have potential energy in state 2 and not have it in state 1. I can make my life very hard and put it some random point and I'll have potential energy both ways, but please don't do that, right? But it all depends where you set your datum, right? Where you define your potential energy to be 0. It doesn't necessarily have to be the ground, right? And you guys hopefully have known that since high school and whatnot. In this case, I'm going to pick my datum to be right here, right? Because, why do I say this? Because this allows my potential energy in state 1 to be 0, right? Because if I draw my initial position, right, where it was when theta is equal to 0, if this is my point G, if I'm going to look at what is the formula for potential energy, for gravitational potential energy, it's mgh, right? In this case, my h is 0, right? So potential energy goes to garbage, right? But then in my state 2, my disk is going to come down here, right? And then my g is going to be here. So my delta h is not going to be 0. It's going to be this distance right here. How do I know this distance right here? What is this distance? It's going to be the radius, right? Do you guys understand that it's going to be the radius? Do you guys see that? Yes. Okay. Beautiful stuff. And then similarly, I could have also put my my datum or where potential energy is 0 down here, right? And then my my potential energy in state 1 would be would have a positive value, and then in state 2 would be 0, right? I could do whatever I want. In this case, we're going to stick to our principles. We're going to say Vg is equal to 0 at this point. So when I go mgh, h is equal to 0. Therefore, this all gets canceled out, right? I'm just left with my kinetic energy at state 2 and my potential energy at state 2. Let's do potential energy because we just covered it right now. We know that potential energy is equal to what formula? My potential energy in state 2 is equal to what formula? mgh, right? Straightforward. Good stuff. mgh. What is h in this case? Yes, sir. It's the negative radius, right? That's very important. This is where negatives and positives come in. You have to make sure that this goes down, right? If you say your datum right here, this is the negative direction, right? So it's negative 0.13, right? Not 0.13, 0.3, right? So if I'm going to plug in my values, right, I'm going to say that my mass is 30 kilograms. My gravitational constant is 9.81 meters per second squared, right? And then my h, as this survey here said, is negative my radius, right? So negative 0.3 meters. We can calculate that in a second. What is my kinetic energy in state 2? What is the formula at least? What is the formula I'm going to use? Yes, sir.
1/2 IIC omega squared.
1/2 IIC omega squared. That is correct. Because in this case, we have pure rotation, right? It's not translating, and it's not doing any fun stuff, right? It's just purely rotating about, in this case, the IC would be this 0.0, right? It would be rotating about 0.0, right? Do you guys see that it's purely rotating about 0.0, right? If I look at G, it's purely rotating about 0.0. Right? It's like a tangential. Like if I had my keys and then I was spinning them around, it's like that, right? Okay. So let's write that down. My kinetic energy in state 2 is 1/2 my mass moment of inertia about 0.0 multiplied by omega squared, right? Which is what I'm trying to find, right? My omega in state 2 squared. Good stuff. Do we have everything to solve this problem yet? Do we have everything to solve this problem yet? Can we find everything to solve this problem? Yes, right? I'm trying to find omega. All I have to do is find my mass moment of inertia about 0.0. What is the mass moment of inertia for a cylinder or a disc that's rotating about like its edge or whatever? I don't know what the heck you call this. If I'm not wrong, it's 3/2, right? 3/2 mr squared. Does anybody want that to confirm that for me? 3/2 mr squared. Yes? Thank you. Beautiful stuff. Do we have this information? Can we find our mass moment of inertia about 0.0? Yes or no? Maybe. And you're confident, yes. Yes, yes, yes. Yeah? Good stuff. Bring this down. It's 1/2 multiplied by 3/2. My mass, 30 kilograms, r squared, 0.3 squared, meters squared. Right? And then this would be omega 2 squared. Right? Okay, you guys have all this information you need. Calculate omega for me. Right? This is your formula. Please calculate omega and tell me what you get. And I'll do it here in the meantime as well. It should be outside of the bracket. You have a number yet?
I got 6.6 radians per second.
Okay. Does everybody agree with that? Anybody get something different? About the same? Yeah. I would trust him too, so just say yeah. Yeah. Okay. So 6.6 radians per second. Yes, radians per second. So that is what I got as well. So from this, once you plug in all your numbers, you're going to get that your omega at state 2 for this disk is going to be equal to 6.6 radians per second. In this case, it would be clockwise, right? So in the negative k direction. So negative k direction. Right? Everybody good with that? Any questions? Once, twice? Okay, good stuff. We're going to go to the second problem, which is a more exciting problem, right? It's much more, going to make us much more alive, awake, yeah? Okay, so the problem reads, the 10 kilogram homogeneous disc shown in the figure below is attached to a uniform 5 kilogram rod, AB. If the assembly is released from rest when theta is equal to 60 degrees, determine the angular velocity of the rod when theta is equal to 0. Assume that the disc rolls without slipping. Neglect friction along the guide and the mass of the collar at B. Okay. So, again, we're going to start with givens, right? In this question, what I can see that we're given is we're given the mass of this disc, right? So we can say the mass of this disc is equal to 10 kilograms. we're given that the mass of the rod is equal to 5 kilograms. And we can not even say mass of rod. We can call it mass AB, 5 kg. Theta 1 is equal to 60 degrees. Theta 2 is equal to 0 degrees. Right? Am I given anything else worth writing down? Probably, but we're going to figure it out through the question, right? Okay. So we're going to go unknowns. What does this question want me to find? What does this question want me to find? Angular velocity of the rod when theta is equal to 0, right? So I want to find, in essence, I want to find the angular velocity of AB when theta is equal to 0. So I can call this angular velocity of AB at state 2, right? In this scenario, it would be very, very helpful for me to draw my schematic of before and after. So let me draw that. Schematic. Right? Let's say this is my ground, right? Let's draw before and after. So before, my thing kind of looks like this, right? I have my cylinder. And then I have my bar, like so. Then I have this guy, like that. This is my point G. This is my point B. This is my point A. Let's put some important dimensions here. This distance is 0.1. This distance right here, for simplicity, it's 0.3 or 0.6 for the whole thing. But let's say this is 0.3 and this is 0.3 meters, right? And then this would be theta, right? This right here angle is theta. Is equal to 60 degrees, right? In my state 2, it's kind of going to look like this, right? In my state 2, when theta is equal to 0, let's say my thing looks like this. And now it's probably most likely not to scale, but this is what it's going to this is what it's going to look like when theta is equal to 0, right? It's going to come down. It's going to go like that. So now this is my B prime. This is still my point G, whatever, right? And this is my A prime, right? This distance is still 0.1 meters. This distance is still 0.3 meters. And this distance right here is still 0.3 meters. Do we agree? And theta is equal to 0. Do we agree with the schematic? Does it make sense? Are we missing anything? I might have missed something. Are we missing anything? Okay, good stuff. Let's draw the kinetics, right? The velocities and the angular velocities and the linear velocities. So we just make it make sense, basically. Our body, if I'm not mistaken, starts from rest, right? Is released from rest, right? So therefore, right now, see, we missed it in givens. We're going to go back and write it so we don't miss it again, right? We're going to say that velocity of AB angularly is 0 in state 1. Angular velocity of my disk in state 1 is equal to 0. My linear velocity of my disk in state 1 is equal to 0. My angular velocity of my disk, or of my rod, or linear velocity of my rod is equal to 0. Well, everything starts from rest, right? So eventually when I get to my formula, it's going to be so beautiful when I get to cancel out that T1, right? It's going to be amazing, amazing, amazing stuff, right? Okay, let's draw my kinetics. Right here, nothing is moving. Do you agree with that? Do you agree that nothing is moving at this state right here? Okay, so everything is 0. Is my angular velocity of my rod, in this case right here, is it clockwise or is it counterclockwise? Right? So clockwise or counterclockwise? Clockwise, right? Because it starts up here and then it's rotating like this, right? It's clockwise, right? So I can draw that. At this case, I'm going to say my omega, AB, is clockwise. Let's call it this. Yep. How about my velocity at point G? my linear velocity, right? Because it's not just rotating, it's also moving, right? Linearly in this case. What do you think my linear velocity is going to look like? Yes, sir.
Going straight down.
It's going to be, at this point in time, yes, it'll be going directly down. We can determine that with kinematics, and we will, but it's going straight down.
Just a quick question.
Yes, sir.
Is the angular velocity of the disk counterclockwise?
That is a very good question.
So why?
Intuitively, no, not of the disk. I'm talking about the rod.
Oh, that's.
This is just for the rod, AB, right? No problem, of course. So this is VG at state 2. How about my disk, which is a very good question that he said. Intuitively, right, it would be going, in this case, it's rotating like this, so it's counterclockwise, right? But I'll give you the spoiler, because I don't think you guys like surprises. You guys are going to get too excited when you guys know, like when we do it and I tell you guys. Right now, the angular velocity is 0, right? And conceptually, if I say it, you'll probably think that as well, right? Because if I explain it, this guy is going down relative to how much that rod is falling, right? But at that point, theta is equal to 0, right? So there's no more, like, and since the rod is attached to the center of the disc, there's no more, like, if you want to call it displacement for that thing to keep moving, right? So at that point, it's going to be 0, right? It's going to stop rotating, right? Because it doesn't have, like, even if that point B, if B prime goes, like theta goes into the negatives, right? That thing's not going to move, right? It's not going to move, right? It's not going to keep going to the left, or your left, at least, right? But if you don't understand that, again, just use the formula. It'll tell you, right? And that's what we're going to do. So even if we do assume that it goes positive or negative or counterclockwise, let's even just say omega of the disk. Let's say we didn't know that. Omega of the disk is counterclockwise, right? That's perfectly fine, right? And it's pure rotation about the IC. Do you guys see that it's pure rotation about the IC, right? Because it's rolling without slipping. Do you guys see that? Or rolling without slipping this way, right? It's always rotating about this IC, right? At all points of time, all points in time, and my IC is changing relatively throughout the motion, right? Okay, good stuff. I think that's all for the schematic. If we want, we can determine. We know that we're going to use conservation of energy, so we can determine the change in potential energy, right, from here to here, right? Remember, oh my God, please do not do this, right? And then find change in potential energy from here to here. Right? Do not do this, right? It has to be about point G, right? The disk in this case we don't really care about because let's say in this case, only the rod is going to experience a change in potential energy, right? Because if this is my initial position, in the next state, my rod is down here, right? So this is my change in potential energy, my change in gravitational potential energy. But for my disk, sure, let's say my potential energy in state 1 is down here, right? In state 2, it's still down here, right? It hasn't changed in the y direction. So therefore, I can put it down, but it's going to cross out from both sides, right? I'm not going to have it on both sides, right? So hopefully that makes sense, right? So this, we don't even need to take account because it doesn't change in the y direction, right? Its position, it's not position, but like its point G, right? Its center doesn't change relative in the y direction. Good stuff. We're going to go to our last step, which is basically solving. You should be splitting this up into further steps, but we're just, we're learning, so it doesn't really matter. But conservation of energy. Conservation of energy. All right, we're going to start with our formula and branch off from there. Let's make this stuff a bit smaller so we can keep the diagram. Any questions so far? You have to ask if you don't understand, please. Right?
So is our
Yes, sir.
T2 0 as well, or just T1?
That's a good question. That's what we're going to figure out. And I'll give you a spoiler so you understand the answer now, and then you see how we get to the answer, right? Just keep it in the back of your head. The disk, since its angular velocity is going to be 0, the kinetic energy in state 2 for the disk will also be 0, right? Because omega is 0. But for the rod is still going to have an angular velocity and a linear velocity, right? So therefore, the rod is going to have kinetic energy, but the disk is not going to have kinetic energy. And we'll see that in this problem. Okay, we're going to start with T1, or Yeah, T1, kinetic energy. And we don't have any conservative forces. That's why it said neglect friction here. And we have the no slip condition down here. So therefore, no kinetic friction, no drag, no anything like that. So we're good. So kinetic energy plus potential energy is equal to kinetic energy plus potential energy in my state 2. Okay. Do I have any kinetic energy in state 1? No, right? Yes, we do not have kinetic energy because everything's at rest, right? Omegas and V's are 0. Beautiful. Do I have any potential energy in state 1? I do. Depending on where you put your coordinate system, right? Or where you put your datum. Where do you guys want to put the datum? You guys want to put it at this or down here? The second way? Yeah, sure, we can do that. This way is a bit more difficult, so we'll go through, or not more difficult, just less, you can't understand it, like it's a bit difficult. Let's just do this way, and then I'll tell you why we're going to do this way. Yeah, okay. But you can do this way. This is the more straightforward method, right? Because here your disk is 0 and your disk is still 0, but even though your potential energy for your disk here and here is not 0, it's going to cancel out for both sides, and I want to show that, right? But you're right. You should do the first way, like this sir mentioned. But since we're going to put our datum down here, or up here, and it doesn't interfere with our diagram, so that's good. We're going to say Vg is equal to 0 joules, right? So therefore, my Vg in state 1 is going to be made up of, my potential energy state 1 is going to be my potential energy due to my disk, plus my potential energy due to rod AB. For rod AB, it's going to be 0. For the potential energy due to my disk, it's going to be mgh, right? In this case, h would be negative. Let's just keep it mgh, let's not solve for it now. Just keep it to the side. This one's 0, doesn't really matter. What's my kinetic energy in state 2? Let's move on, and we'll come back to this and show you why it's 0. What is my kinetic energy in my lovely state 2? Yes?
General plane motion equation.
Yes, exactly. Exactly. And that's for the rod. How about for the disk?
There's no motion at state 2.
There is no motion at state 2, but we're going to show that, right? So let's assume there is, right? And the motion at state 2, if let's say you didn't know it was 0, it would be purely rotational. Do you agree with that? Right? About the IC. You don't have any translation because there's no slipping at the IC. Do you agree with that? Perfect stuff. So we're going to have some kinetic energy due, because if we didn't know, kinetic energy due to my disk plus kinetic energy due to my rod, or AB. The kinetic energy due to my disk is going to be purely rotational, so that's going to be 1/2 my moment of inertia of my disk about my IC multiplied by my angular velocity of my disk, right? Squared plus the kinetic energy, like you said, general plane motion, right? We have to account for the rotation and the linear velocity of my disk, or the linear potential energy, or not potential, I keep saying potential, kinetic energy of my rod, and therefore that's going to equal 1/2 m of my rod, AB, v about my point G squared, plus 1/2 my mass moment of inertia about my point G. Yeah, we can do it about point G. About my point G. Yeah, about my point G. I think it's about point A. I'm not sure. We'll get to it. Omega squared, right? Of AB squared in state 2. Is it good up to now? Do we understand up to now? Yes, no, yes.
I'm just wondering, is it about the mass moment of inertia, is it about point G, or would it be about one of the ends?
I'm sure it's going to be about point G, but we will determine that through the question. I'm not completely sure. If anything, I'll look at the answers. Let's see. Yes, it will be about point G. We can do it about the ends using parallel axis theorem, but the common rule is about point G. If we want, we can change it, but in this case, we don't have to, right? And we'll see that. So just always stick to this general formula, and then if you see something, because it isn't purely rotating, right? If this rod, for example, was doing, like, screw this disc, right? And then make this point fixed, right? And then say this rod was rotating like this, upward. then it would be purely, the rotation would be purely around point B, right? Then you would use the mass moment of inertia. Instead of 1 over 12 ml squared, you 1 over 3 ml squared, right? If that's correct, I don't know. Something like that, right? But in this case, we have general plane motion, right? So we need velocity and angular velocity. Anyway, which lovely guy do I want to do first? This is going to be fun. Well, okay, let's start with this guy. All right, let's go ahead with finding this guy. This stuff for V2 potential, or actually let's go through this. Let's branch off and then let's follow through with the steps later on, right? So this is how our approach is going to be for solving our potential energy or our kinetic energy in state 2. How about the potential energy in state 2? Well, the potential energy in state 2 is simply going to be the change, right? This change in height of our rod, right? It's going to be mg, the displacement of our point G, right? How can we find this displacement of point G? How can we find this distance right here? Yes? Beautiful, yes, exactly, right? So we're going to use this angle 60 degrees, right? And this this length, 0.3 meters, and therefore, what trig function relates these two? Sine, yes, amazing, right? So it's going to be 0.3 sine of 60 degrees. What's sine of 60 degrees? Sine of 60 degrees. Root 3 over 2, right? 0.3 multiplied by root 3 over 2. We keep going. This can be 0.15 multiplied by root 3. You guys see that, right? So this is my change in height. Since I'm going below my datum, I'm going to make it negative, right? So it would be negative, right? Do you guys understand why it's negative? Yes? Okay. You guys look a bit lost. I need confidence. I need yes. Okay, good stuff. Okay, so that's how I find my mg, right? Fairly simple. Let's use a different color. mgh of my rod, AB, about my point G, right? This is going to be 10 kilograms. Is it 10 kilograms? I don't know. 10 no, it's 5. 5 kg multiplied by 9.81 meters per second squared multiplied by negative 0.15 multiplied by root 3, right? And that's all the potential energy, the gravitational potential energy we have in our state 2. Do you guys agree? Yes. Thank you. Yes, that's good. It still has potential energy, as he just said. It would have the exact same thing, right? It would also be, since we chose to make our datum up here, the wheel still has potential energy, right? And it would be the exact same distance. Instead, it would be m, g, h, in this case, m of the disk, right? So 10 kilograms multiplied by g, 9.81, multiplied by this change in height, right? Which we determined to be negative 0.15 root 3. But look at my state 1. Since I accounted for potential energy in my state 1, I didn't even need to solve this, right? I know that I have the exact same positive term on both sides. Or in this case, it would be negative because negative h, right? Because you're going down, right? But it's negative on both sides, so therefore it cancels out on both sides, right? So I didn't even need to calculate it. And that's the exact same thing. And no, it's not the exact same thing, but the point is, we're not looking at necessarily the potential energy in state 1 and 2, but we're looking at the change in potential energy, whether it differs, right? And that goes back to the concept of whether work is done from a state to another state, right? Whether you travel through a path, right? Which we did last time. But regardless. So from this, we realize we're going to cross this out since same in V2. Good stuff. Thank you for that. Okay, let's go ahead with finding this stuff. And at this point, it's literally just what you have been doing for the first half of the course, right? It's just relative velocity analysis, or I don't know what it's called. But yeah, let's start with this lovely term and determine that it's 0. Okay, I'm not going to spend too much time on this because we have we have another question to go through. So I'll ask you guys, but if you have any questions, please speak up, right? If there's anything that you don't understand. Okay, I want to find this guy, right? Let's start with finding omega. I have what like in the back of my head, I always want to know what I want to find. I don't want to go ahead and find everything and then what do I need to find again? I don't want to do that, right? I want to find the things, I want to isolate the one that I know that I have to find in the end. And that guy is right here, right? My two unknowns in this moment in time is my velocity at point G as well as my angular velocity of my disk, right? I don't know it yet. I know it's going to be 0, but I don't know it yet, right? Okay, let's find this guy. And let's just neglect the fact that it's squared. Let's literally just find omega, right? Okay. I think it's easier to explain here. I want to find omega, right? Of my disk, right? I assume in this case it's clockwise or counterclockwise or clockwise, which is negative k, right? I know that I can say that my velocity at A at this instant in time, right, is going to be going this way, right? Or before we even do that, we can just we can find this omega using relative velocity when finding velocity relative to my IC about point G, right? And that is simply because we have the no-slip condition, right? That is simply this thing right here. I know that my velocity at A, or A prime in this case, is equal to my velocity about my IC, right? Plus omega d cross R A prime with respect to my IC, right? Do you guys see that? Any questions? My IC is moving or not moving? I'll give you a clue. It's called instantaneous center. It's not moving, right? I'm picking a new IC at each moment, right? This allows me to simulate pure rotation if there's no slip condition, right? So therefore, this goes to 0, and I'm left with the common formula which relates angular velocity and tangential velocity, and that is this guy, right? I see, right? Let's write it down. VA is equal to omega d cross R. I'm trying to find omega d, so I can say that omega, or let's just keep it like this, right? Let's find another formula that uses this omega d, right? I can also relate VA, the velocity of A, which is purely in the negative I direction in this case, with the velocity of B, which I know is directly going downwards, right? Do you guys agree with that, right? Okay, let's write that down. The velocity at A is equal to my velocity at B plus my angular velocity of what? Of the disk or of AB? Of AB, right? Right here to B, I'm looking at the angular velocity of AB, right? Of AB cross R, and we forgot this. This is A with respect to IC. This one is A with respect to B. In this case right here, I can set these two equal to each other, right? Can I do that? Yes or no? I can do that, yes? Let's put it over here. I can say that omega d cross R with respect to my point A with respect to my IC is equal to my velocity at B plus omega AB cross R to A with respect to B. What I like to do at this stage is I like to bring my marker or whatever, and I want to indicate, what the heck happened? I want to indicate all the directions that I have, right? All the directions that are known. I know that, or at least I assume that omega, my angular velocity of my disk, acts in the clockwise direction, right? And is that negative or positive? K. Negative K, right? So I'm going to just say in the back of my mind, just organize myself, because this is where the mistakes come, right? The negatives and the positives and the directions. Negative K. Okay. How about R? My radius from A, from my IC to A. What direction is that in? From this point to this point. It's pointing up, right? So it's positive J. So positive J. How about my velocity at B? My velocity at B. negative j, right? Negative j. My angular velocity about AB, of my rod AB, negative k, yeah. My position vector. What do you think? 2A with respect to B. So is it pointing this way or this way? 2A, yeah. Beautiful. 2A with respect to B, right? So negative I. Now we do the fun, right? We started wiggling our hands around with the directions, right? Okay. What is negative K cross J? Right hand rule. Yes, sir. Positive I. So if this is your coordinate system, right? J is going up, I is going like this, negative J, positive negative I, right? K is coming at you, positive K is coming at you, negative K is going into the screen, right? Do you understand? Negative K is going into the screen, positive K is coming at you. What you do is, in this case, it's negative K cross J, right? You go negative K, right? Cross, J is going which direction? Negative J, positive J. J is going which direction? Up, right? I turn my hand up, right? My thumb points in what the cross product equals to, right? In this case, like he said, it's I, right? So this one is going to become I hat, right? What other product do we have? Negative K, right? Again, negative K into the screen. I roll my fingers in the direction I want to do the cross product in. Oh, it's up here. I'm looking. Okay. Negative K into the screen. Negative I, right? And then my resultant vector is going up, right? So negative K cross negative I is positive J. Let's add positive K cross I, right? Positive K, I, going this way. Therefore, my answer is positive J. Negative K cross negative I, it's positive J, right? I don't know. That's the whole jazz, but you guys probably did that already, so we won't spend too much time. So this is going to be positive J. Do you guys agree? Right? Good stuff. I can keep going. From this, I'm going to get that my omega D multiplied by R with respect to A over to my IC. Actually, we can fill up this value right now. What is this? What is my position vector from 2A with respect to my IC? My position vector, 2A with respect to my IC. 0.1 meters, right? My position vector, 2A with respect to my IC is simply the radius, right? And I already did the direction, so I don't have to worry about that right now. So it's 0.1. 0.1 in the I direction. This is going to equal my velocity of B in the negative J direction. So let's say negative VB in the J direction plus omega AB multiplied by what is this vector, this position vector? A with respect to B? Just the magnitude. 0.6. Is it 0.6? Do you guys agree? Are you sure? Are you sure? Confidence. Yes. Good job. It's 0.6. J. What I can do now is I can split up my I components and my J components, right? Therefore, I know that 0.1 in the I direction, if I take first off, 0.1 omega D is equal to 0, right? And this is how I determine my angular velocity is equal to 0, right? And then if I look at the J direction, if I rearrange some stuff, I know VB is equal to omega AB, or to 0.6 omega AB, right? Good stuff, right? So in this whole process right here, we determine two things. We determine, number one, that my angular velocity of my disk is equal to 0, right? Which makes my kinetic energy of my disk equal to 0, which confirms our assumption, which we made in the first givens or whatnot. And then the second thing that it does is it gives us a formula to work with, right? For relating our velocity at point B, right, which is purely in the negative J direction, with our angular velocity of the rod. But let's zoom out a bit, take a deep breath, and then go back in, right? Okay. Since angular velocity of our disk is 0, all of this goes to garbage, right? Bang. We're done with that. We can keep going. I want to find VG, right? I have this formula in the back of my head that I found, right? I can use this later if I need to. I want to find VG. How do I find VG? Well, again, relative velocity analysis or whatever you call it, right? We're going to come down here. We're going to have to use this diagram again. I'm sorry, but it's atrocity right here. We're going to say that I can relate VG with something I already know, which is VB, right? How would I relate VG? How would I relate my velocity? What is VG equal to? Yes, sir.
Would it be equal to VB plus omega AB cross R of B with respect to G? Or G with respect to
Yeah.
B?
Good. Thank you. Beautiful. He's right. What direction is VB acting in?
Negative J.
Negative J. What direction is omega AB acting in?
Negative K.
Negative K. What is the direction vector, the position vector, to G with respect to B?
Negative I.
Negative I. What is negative K cross negative I? Oh, it's in the corner. My bad. You guys need to tell me. What is negative K cross negative I? Positive J, right? Right? I simplify this further. I get VG is equal to VB. I can directly sub in, right? Which I got from this last equation that I did, right? I can sub that in for VB right now. I can say that VG is equal to 0.6 omega AB, right? And again, this is in the J direction, right? If you want to be specific. Plus, what is my position vector magnitude from 2G with respect to B? What is the magnitude of that? 0.3. Are you sure it's 0.3, guys? Are you sure?
Yes.
Check it again, please. It's 0.3? I need more nods. I need confidence.
0.6.
Is it 0.3 from G with respect to B? Yes, right? Okay, yeah. Because don't seem confident in your answers. 0.3 multiplied by omega AB, right? And this is in the positive J direction, as we said. If I add these two lovely guys, I'm going to get, 1 second, please. We're going to get 0.9 omega AB, which seems a bit off to me. I remember 0.6 omega AB when I was doing this question. Let me check something out, please. And you guys also look for a mistake. I might not be wrong, but just in case. No, I think we're on the right track. I think we're good. Okay. So this is my answer, right? 0.9 omega AB, right? We're good up to this point, right? Yes. For VB, I wrote that it's negative J. Thank you. That is my mistake. Thank you very much. Yes, because it says 0.3 here, and I was like, I'm confused. Thank you very much. So she's right, right? It's negative J. So I sub in this negative J. No. I sub this one in, and then it's in the negative J direction. So this is negative, right? And then I add, right? Negative 0.6 to 0.3. So this is negative 0.3. And that would make sense in the J direction. Do we agree now? Yeah? You guys need to catch my mistakes. Thank you very much. I appreciate it. Right? Okay. Good stuff. We have negative 0.3 omega AB. Good stuff. Do we have everything we need to solve this problem now? Right? Let's recap. We initially said, from this conclusion here, that all we have to do is find my kinetic energy in state 2 and my potential energy in state 2. My kinetic energy now, we know, is equal to 1/2 m of my rod, right? Multiplied by the velocity, the linear velocity, right? And that is, we found to be negative 0.3 omega AB, right? Squared. Do we agree up to this point, right? Good stuff. Plus 1/2 my mass moment of inertia about point G. We should have found this before because I don't want to waste time finding it now, but long story short, it's 112 my mass of my rod, so MAB, multiplied by my length of my rod squared, which is 0.6 meters squared, right? So that's my mass moment of inertia about point G. And then also multiplied by my angular velocity of AB, right? My angular velocity of AB. And that simply is what we're trying to find. So angular velocity of AB squared. Plus the potential energy, right? And in this case, the potential energy is negative, so we can just put it down as a wonderful negative value. So 5 kg multiplied by 9.81 meters per second squared, multiplied by 0.15 square root 3 meters. Right? Do we have everything we need to solve this problem? Right? We're trying to find omega AB. Do we have everything we need? Yes? Okay. Factor omega AB out from this and tell me what answer you get, please. Do we have an answer yet? Do we have a number yet? No? It's okay, I expect the last time I asked you guys to multiply two things together, it took you guys a while. So it's okay.
6.5.
Pardon?
You got 6.5.
That's what I got as well. Nice job.
There is one thing, there is no mark for it, so that's why.
Oh, there's no bonus marks, that's why, huh? If you guys don't give me an answer, I'll tell her to give you negative marks. How about that, huh?
Getting ready for the exam.
Exam's easy, don't worry.
That's what I was gonna ask. Like, this question, for example, this is like really long question. Is it coming in the?
No, it's not a long. It's only long because I'm going through it. I'm explaining each step. No, but in reality, if you know what you're doing, all these questions is literally formula, right? T1 plus V1 plus is equal to T2 plus V2, and just branch off from there, and then you solve it, right? All of them, right? All of these questions, even conservation of momentum, is the exact same thing once you get to it. Or work energy theorem, which we already did. It's just the formula. Make sure you don't screw up with positive and negative, and you're good, right? It's literally the formula. And she always said this to us as well. Like, if you don't understand, like, the concept behind it, you have the formulas right there, right? You just use the formulas, right? At the end of the day. Make sure it's positive or negative. But regardless, you guys will do fine. 6.52 radians per second. What direction is it? Negative K. Right? Clockwise. Good stuff. So that is how we do this lovely question. I don't believe we're going to have time to go through the next question because it's fairly long. But long story short, this is a very good practice problem to try, and she may cover it next week. But it's the exact same thing, right? In this case, the only potential energy that you will have is due to the spring, right? And then to find this potential energy is 1/2 kx squared, right? You want to find this change in the change in length of the spring, and we'll go through that part, just that part. That part's the only difficult part, in my opinion, of this question, right? Just the change in length of the spring, how much this guy stretches, right? So, and then the rest is literally gravity and what you've been doing for I don't know how long in physics, right? For so long. The only kind of difficult part of this question is finding this change in length of the spring, which we'll do very quickly. So, I know that in state 2, long story short, everything starts from rest, whatnot, blah, blah, blah. In state 2, this is going to rotate, right? And then it wants me to find, in state 2, my potential energy due to my spring, right? There's other potential energy, there's gravity as well, but there's also potential energy due to the spring, and that's simply 1/2 kx squared, right? I know that my stiffness is 75 pounds per foot, right? And then my x is, in this case, if I call this point right here, let's call this point right here A, right? Let's call it point A. Let's say in state 2, it rotates and it shifts to A prime, right? And then the change in my displacement, how much my string stretches is simply just the change in position of my point A. Do you guys agree with that? Right? How much my string will stretch is just the change in position of my point A. So I can say that SA is equal to how much the displacement of my string stretching, right? Or my spring stretching, right? Okay, how do I find my displacement about point A? I know that about my point O, which is a fixed point right here, my velocity, VA, is equal to VO plus omega cross R, right? Again, nothing's moving, right? I just put VO there for technicality, but nothing's moving, so this is the formula that you know and love. I integrate this formula, which I get another formula, which I know and very much love, is my change in displacement of point A is equal to my theta, right? Because I'm going backwards in time, right? Angular velocity. If you're going to derive, it would be acceleration, right? But we're going back, so it's position, right? Multiplied by my radius. In this case, it would be A with respect to O, right? So this is what I sub in for X right here. You might be asking, how the heck do I get theta? Well, theta can be easily determined. Let's firstly write this down quickly. So we said this is going to be equal to theta at my state 2 multiplied by my position vector, which is O, which is given, right? 0.75 feet, which is A with respect to O, right? My only unknown in this case is my theta. How do I find my theta? Well, I can determine it by looking at, do you agree that this inner disk will have the same angular velocity and same angular displacement as the outer disk, right? Because they share the same axis. Do you agree? Right? They rotate at the same speed and they'll have the same angular displacement. Well, I can find theta 2 pretty easily for my outer disk, right? And how do I do that? Well, the question tells me that this line right here will descend a delta S, if this is my point B, right, and this was my initial point B, this is point B, and this is my B prime, this arc length, if you will, that block will descend 5 feet. So therefore, I can say that my arc length, or we call this formula arc length, but in essence, it's just SB, right? My change in position of my point B is equal to my position, or let's use velocity first and then go from there, right? So velocity of my point B is equal to my velocity of point O plus my angular velocity cross my what do you call it? My position vector of point B with respect to O. Agreed? Yes or no? Yes, right? VO is 0. It's fixed, right? I get this equation. I integrate it. I get SB is equal to theta R cross, or RB with respect to, I always get this wrong. Okay, B with respect to O. I know this value. I'm trying to find theta. Do I know SB? Yes, I do, right? Because it descended, that block has descended 5 feet. So therefore, if I look at this arc length right here, this would be 5 feet, right? Now it's just straight, right? So it descends 5 feet. So this one's also 5 feet. I rearrange this lovely guy. I say theta is equal to SB over R. Therefore, it is equal to 5 feet over what you call it? I think it's a 0. No, not point 0.75. Yes, you're correct. Thank you. 0.075 or 0.75 feet. I do this calculation. 5 divided by 0.75. It's 6.6666 blah blah blah, right? Theta is equal to 6.66667 degrees or radians. There's only one right answer. I heard a whisper of degrees. Please do not do that to me. It has to be radians, please. It has to be radians, right? Just joking. Right? We plug this lovely formula into here, right? Because again, we said that the change in displacement, or the angular change in displacement, is the same for the inner circle and the outer circle, or the inner disk and the outer disk. Into this formula, yes?
Where did you got that 5 feet?
5 feet, it was given in the question. The question tells me that this box, it starts here, and then it descends, it goes down 5 feet. Right? So this rope is extending, and therefore, if it goes down 5 feet, that also means that this disc angularly, if I look at the arc length, it also has traveled 5 feet in this curved direction, right? And then it becomes straight. But long story short, I plug these lovely numbers in, right? 1/2, 75, 6.6667, right? Radians, 0.375 feet. And then I get my lovely potential energy due to my spring. But that's the only difficult part from what I remember in this question. And then in terms of the positive or negative, if you keep stuff in order, it takes care of it, right? But just stay aware. And you can also do this problem if you want with work energy theorem, which we did last time. It's fairly simple. Instead of saying that this goes down, right, you're just going to bring this concept that, okay, there's a force here that's causing work, right? Or there's a moment, if you will. But regardless, yeah, and that is,
Another question
yes.
about that power of 2. Where is that power of 2 goes?
The power, yes, you're correct. Thank you. Yes, you're correct. I missed it. So it should be squared. Squared. And then that's how you would go ahead with solving this. So I'm going to stop the recording, and then if there are any questions, and if